This is the second meeting on this very short series of talks on Lanford's theorem. So last week we had Giovanni Valente from Milan. I hope you had a chance to see the recording if you were not there, because I guess it's going to be useful to follow today's talk too, because mainly Vincent Ardourel is going to give a reply to Joachim and Valente's paper. So yeah, here we go. I'm happy to have Vincent here. Thank you for accepting the invitation. You can go whenever you want, and I'll warn you in 45 minutes.
Okay. Thank you, Christian, for your kind invitation. I'm very pleased to talk after Giovanni, who presented his work last week on Lanford's derivation of the Boltzmann equation. So Giovanni cannot be here today, but in a sense will be with us, since I will talk about him a lot. My talk is indeed a reply to his paper, and this talk is based on a paper I published 4 years ago in 2017, after reading yours, you think, and Giovanni's Valente's paper. By the way, I thank Giovanni very much for the talk he gave last week. He presented many technical details on Lanford's derivation, and that's great. It will be very helpful for my presentation, which should be less technical. And the last point, don't be afraid by the number of slides. All are not included in my talk. So to begin with, a few words of introduction. The problem of irreversibility is, of course, a long-standing issue in the philosophy of physics. And I think it's nicely formulated in Reichenbach's books, The Direction of Time. The macro processes are irreversible, as we know. How can this irreversibility of macro processes be reconciled with the reversibility of micro processes? It's a paradox which a physicist has to solve if when he wishes to account for the direction of thermodynamical processes and for the direction of time. So we will discuss this problem, but in a more specific context. I mean, in the case of hard spheres gas. So let's consider a gas of hard spheres. At the microscopic scale, the time evolution of the gas can be described with the Boltzmann equation. This equation is irreversible in the sense that it's not invariant under time reversal. If we transform t into minus t, we don't have the same equation. And this equation is also irreversible in the sense that a mathematical function called the minus h function, which depends on the solution of the Boltzmann equation, can be viewed as the entropy of the gas. The solution of the Boltzmann equation evolves in such a way that the minus h function increases with time. And this is the famous H theorem. By contrast, at the microscopic level, hard spheres evolve according to the laws of classical mechanics, such as Hamiltonian equations, which are invariant under time reversal. So the question is, how can a set of reversible equations lead to an irreversible equation? So Boltzmann's historical derivation has been extensively discussed in the history and philosophy of physics. In particular, it has been argued that Boltzmann's derivation was not satisfactory. More precisely, some time asymmetric ingredients are introduced into the derivation to obtain an irreversible equation. So this historical derivation is more a heuristic derivation, but not a well-grounded mathematical derivation. In this talk, I will not discuss the original Boltzmann's derivation. I am interested in contemporary works on the Boltzmann equation. So as we said last week, Lanford provided in 1975 a rigorous mathematical derivation of the Boltzmann equation. The main idea, due to the mathematician Grad, is to study the gas in a limiting regime for which the number of particles tend to infinity. And this derivation is a very important topic in mathematics. It involves many mathematicians such as Giardiniani, Isabelle Gallagher, Laure Saint-Raymond, among others. And these works are very stimulating because some major philosophical problems with the historical Boltzmann's derivation seem to vanish with Lanford's derivation. For example, the controversial hypothesis of molecular chaos, or Stochastic, which is required in the heuristic Boltzmann's derivation, is no more required in Lanford's theorem, Lanford's derivation. And I will go back to this point later. So here I put some quotations to illustrate the importance of Lanford's derivation. For example, on the problem of irreversibility, John Herman says, I am convinced that the most fruitful approach is to concentrate on rigorous derivations of the Boltzmann equation. Let's hope that the progress in this area is not as slow over the next 100 years as it was over the past 100. For Herbert Spohn, the Boltzmann equation is still the cornerstone of the kinetic theory of gases. Lanford gave a proof. This is one of the gems in the field. And as we said last week, for Cédric Villani, Lanford's theorem is maybe the most important mathematical result of kinetic theory. So this talk deals with the philosophical consequences of this derivation. Jos Ufink and Giovanni Valente, as you know, provided a very insightful analysis of this mathematical derivation. After several decades of discussions, mostly between physicists and mathematicians, Ufink and Valente aim to answer the question, will anyone say exactly what Lanford's theorem proves? And here the main claim of their paper. We discussed the problem of the emergence of irreversibility in Lanford's theorem. We argue that all the different views on the issue presented in the literature miss the target, in that they fail to identify a time asymmetric ingredient that, added to the Hamiltonian equations of motion, would obtain the Boltzmann equation. More to the point, we argue that there is no such an ingredient at all, as one can infer from the fact that the theorem is indeed time reversal invariant. My talk is a follow-up on this paper. I hope to offer some contributions to this analysis, despite the fact, I have to say, that all what I know on Lanford's derivation mainly comes from Ufink and Valente's paper. In this talk, I claim that in some sense, we can identify a time asymmetric ingredient. To be clear, I fully agree with Ufink and Valente's conclusion on the fact that Lanford's theorem is time reversal invariant. However, I would like to suggest another perspective or another interpretation of this derivation. More precisely, I will analyze two mathematical tools discussed in the paper. First, the Boltzmann Grad limit, which is the limiting regime used to derive the Boltzmann equation. Secondly, the use of incoming configurations, which is a way to represent collisions between particles. Roughly speaking, my claim is that these two mathematical assumptions are crucial to to obtain the Boltzmann equation. And more specifically, I claim that the incoming configuration taken with the Boltzmann Grad limit is the time asymmetric ingredient that allows one to obtain the Boltzmann equation. In other words, I claim that there is a twofold time asymmetric ingredient which comprises the Boltzmann Grad limit and the incoming configurations. So my talk is organized as follows. First, I will present Lanford's derivation of the Boltzmann equation. Then I will stress why Lanford's theorem is so important. I mean, how it avoids the objections addressed to the original Boltzmann's derivation. After that, I will turn to the core of my talk. I will analyze the role of the two ingredients in the emergence, in the appearance of irreversibility in the derivation of the Boltzmann equation. First, the Boltzmann Grad limit. Secondly, the incoming configurations. And finally, I will offer some concluding remarks on my analysis of Lanford's derivation. So even if Giovanni already presented Lanford's derivation last week, I think it's important to recall at least the main steps of the derivation. So we consider n identical Hart spheres with mass m and diameter a, which move freely according to the laws of classical dynamics. We denote by q and p the position and the momentum of the center of the spheres. And as you can see in the figure, two spheres, 1 and 2, collide when the relative position of the spheres, the vector omega 1, 2, equals the diameter a. In that case, the velocities change in accordance to the conservation laws of classical mechanics. Otherwise, if they do not collide, they keep the uniform motion. So as we know, this microdynamics is time reversible and deterministic. Now, let me see how the Boltzmann equation is derived from this reversible and deterministic microdynamics. The derivation requires different main steps, I mean 4 steps, which I will sketch very briefly. I will not enter into mathematical details, and here some references for technical details. So the derivation begins with the Liouville equation of the n Hart spheres system. In Hamiltonian mechanics, the Liouville equation describes the time evolution of the probability density mu to find the system in the phase space. Here, h is the Hamiltonian of the system. And the Liouville equation is reversible. I mean, it is invariant under time reversal, just like the Hamiltonian equations. The aim of Lanford's derivation is to obtain, of course, the Boltzmann equation from this Liouville equation. More precisely, Lanford's derivation aims to prove that some under conditions that we'll discuss later, the solutions of the Liouville equation tend to the solutions of the Boltzmann equation. So here's the Boltzmann equation. We discussed this equation last week. The function f represents the probability density of one particle. And there are two terms that are responsible for the time evolution of the function f. I mean, a free transport term on the left, and most importantly, the collision term q on the right, which describes the collisions in the gas. To obtain the Boltzmann equation, we use an intermediate step, I mean a mathematical framework called the BBJKY hierarchy for 5 mathematicians, Bogolyubov, Born, Green, Kirkwood, and Yvon. The BBJKY hierarchy is just a reformulation of the Liouville equation. It is a set of n integral differential equations which are equivalent to the Liouville equation. Here are the equations of the BBJKY hierarchy. They relate to reduced probabilities rho k, which are the probability densities for k particles among n. That's why we have n equations. The first equation of the hierarchy describes the time evolution of the probability density for one Hart sphere, which depends on the probability density of two Hart spheres in the collision term Ca. The second equation of the hierarchy describes the evolution of the probability density of two Hart spheres, which depends on the probability density of three Hart spheres, and so on. This hierarchy of equations is the Liouville equation applied to rho 1, rho 2, rho k, and so on until the last rho n. So this hierarchy is a chain of n interconnected integral differential equations. An important point is that the Liouville equation and the BBJKY hierarchy are both time reversal invariant. They contain the same information on collisions. They are, in that sense, equivalent. And this is a very important point. The BBJKY hierarchy is time reversal invariant. Okay, there is another step in the derivation. It's the Boltzmann hierarchy, which is the BBJKY hierarchy when the number of particles tend to infinity. More precisely, we use the Boltzmann Grad limit and not merely the infinite limit. I will go back to this point later. The Boltzmann hierarchy is also a set of integral differential equations, but since the number n of particles tends to infinity, the number n of equations also tends to infinity. And importantly, unlike the BBJKY hierarchy, the Boltzmann hierarchy is no longer time reversal invariant. So the step between the BBJKY hierarchy and the Boltzmann hierarchy breaks the time reversal invariance of the equations. The Boltzmann equation is finally obtained after a last step, which makes use of a factorization condition. The probability density for k particles is factorized with the probability density of one particle. I will go back to this point too. So under this condition, the Boltzmann hierarchy leads to the Boltzmann equation. So again, the important point is that the Boltzmann hierarchy and of course the Boltzmann equation are not time reversal invariant. They are time reversal non-invariant. So the property of time reversal invariance has been lost between the BBJKY hierarchy and the Boltzmann hierarchy. So I think we have to focus on this step. Within this derivation, what we call Lanford's theorem is the following result. Roughly speaking, very roughly speaking, it states that under some mathematical conditions, on the initial conditions and on the regularity of functions, the solution of the BBJKY hierarchy tends to the solution of the Boltzmann hierarchy. And this convergence is proved in the Boltzmann Grad limit, which is a limit where the gas is very diluted, infinitely diluted, and the number of particles tend to infinity. As I said in the introduction, it's a very important theorem for the kinetic theory of gas, even if the time validity for the convergence is very small, around 1/5 of the mean free time. It's very short, a few milliseconds for real gases. And this very short time validity has been criticized. However, as Giovanni said, this time validity is due to some convergence requirements, which might be modified in the future. I mean, the proof might be extended in time. Moreover, from a in principle point of view, from a conceptual point of view, Lanford's theorem is still very important and very informative since, strictly speaking, it allows one to obtain the H theorem. I would like to stress an important property on which I will go back later. Lanford's theorem is time symmetric or time reversal invariant. From an initial condition, t equals 0, the theorem is valid for a time interval symmetric with respect to this initial condition. More to the point, this theorem allows one to derive the Boltzmann equation for positive times, but also to derive an anti-Boltzmann equation, a backward Boltzmann equation for negative times. So for positive times, the minus h function or the entropy S increases with time, and for negative times, the minus h function decreases or the entropy decreases. So Lanford's theorem is time reversal invariant in that sense. However, it does not follow that there is no time asymmetric ingredient to obtain the Boltzmann equation with Lanford's theorem. And I will argue that there is such a time asymmetric ingredient, which is the ingoing configurations. But for now, let's go back to the derivation of the Boltzmann equation. The important point, again, is that the BBJKY hierarchy is time reversal invariant. And by contrast, the Boltzmann hierarchy and the Boltzmann equation are not time reversal invariant. Lanford was very clear on this point. The BBJKY hierarchy is time reversal invariant, but not the Boltzmann hierarchy. So in 1975, this point was very clear. So irreversibility seems to appear between the BBJKY hierarchy and the Boltzmann hierarchy. At least time reversal invariance disappears between the two hierarchies. Actually, there is a difference between irreversibility in the sense that entropy increases with time and being time reversal non-invariant. Indeed, equations can be time reversal non-invariant even if the entropy decreases with time. And as I said, this is a case for the negative times with Lanford's theorem. And again, I will go back to this point. My point is that there are two main assumptions or mathematical ingredients to derive the Boltzmann hierarchy from the BBJKY hierarchy. These two ingredients are discussed by Fink and Valente in their paper. They are Boltzmann Grad limit and incoming configurations. However, before analyzing the role of these two assumptions, I would like to stress, to highlight why Lanford's derivation is so important for the problem of irreversibility. Very briefly, I would like first to make clear that Lanford's derivation avoids the reversibility objections, also called the Loschmidt objection or paradox. As you know, the objection is the following one. Consider a gas initially in the left part of a box, then the gas freely expands, and at some time, T2, we reverse the velocities of all particles. In that case, the gas will return to its initial state. All particles will go back to the left part of the box. And this evolution between the time T2 and T4 does not satisfy the H theorem for positive times. The minus H function, or the entropy of the gas, decreases with time. So this point has been extensively discussed in the literature based on the original heuristic Boltzmann derivation. And here I would like to see what happens with Lanford's derivation. We discussed this point last week, so I will be very brief. Lanford's theorem seems to avoid this kind of objection. The velocity reversal transformation does not hold with Lanford's theorem. And Vincent and Valente have made this point very clear. We cannot apply Lanford's theorem after velocity reversal to obtain an evolution during the time t to t. An argument along the lines of the reversibility objections against Lanford's theorem is thereby blocked. Indeed, for convergence reasons, it's not possible to apply Lanford's theorem after velocity reversal. And Giovanni discussed this point. This is due to the sets on which we can prove the convergence of the BBJKY hierarchy to the Boltzmann hierarchy. The size of these sets decreases with time. And let me illustrate this point with this figure taken from Bodino and his colleagues' paper. Time validity for Lanford's derivation is T star. So we start with the initial condition T equals 0, and the time validity is T star. So we derive the Boltzmann equation from the initial time 0 until the time tau. And the question is, can we obtain the Boltzmann equation at the time tau prime starting from the time tau? So can we go backward in time? The answer is no. We cannot go back to the Boltzmann equation at the time tau prime. And these mathematicians are very clear on this point. We cannot prove the convergence of the reverse Boltzmann dynamics on the interval tau prime tau starting from tau. For the same reasons, the argument behind the so-called Loschmidt's paradox fails. Indeed, at the time tau, we reverse all the velocities. So if we invert or reverse all the velocities, we have the same situation. We cannot apply Lanford's theorem for the same convergence reasons. So the conditions that allow the BBGKY hierarchy to converge the Boltzmann hierarchy are not the same at the time 0 and at the time tau. However, what's important is that the convergence can be proved for a forward time interval. It's indeed possible to derive the Boltzmann equation starting from tau for a forward time t tau prime. And this is called the time concatenation property. So therefore, we can move forward in the derivation, but we cannot move backward. Secondly, Lanford's theorem does not require...
Sorry, may I ask a question?
Yeah, of course.
I was thinking, I thought like tau was limit time of validity, but if you can concatenate, it would imply in the end there's no really time limit because you can concatenate as much as you want, or?
Maybe I wasn't clear. It's not the time validity. The time validity is T star. So
okay.
Yeah,
oh,
so
yeah, okay.
To be in the time validity.
Okay, thanks.
Yeah, after T star, you cannot do that. So so it's T star and tau prime is before T star. So we have made some progress with Lanford's theorem since there is no objection in this sense, no reversibility objection. And secondly, I would like to discuss another point. Lanford's derivation does not require the controversial assumption in the historical Boltzmann's derivation, that is the Stossal ansatz. It is the assumption of the number of collisions, also called the molecular chaos hypothesis. And so roughly, this hypothesis states that two particles that are going to collide are uncorrelated. And again, Ufink and Valente have made this point very clear. Concerning the historical Boltzmann's derivations, they say that the irreversible time evolution of macroscopic systems cannot be a consequence of the laws of Hamiltonian mechanics alone. As we now know, the Stochastic is the culprit. So the Stochastic is the time asymmetric ingredient added into the Hamiltonian equations in the historical Boltzmann's derivation. And let me clarify this point. Ufink and Valente have shown that we must distinguish between two different conditions within the Stochastic. The Stochastic comprises a factorization condition and a pre-collision condition. Yet the time asymmetric ingredient is the pre-collision condition, not the factorization condition. Indeed, the pre-collision condition makes reference to a direction of time. It describes what happens before collisions. However, the factorization condition does not make reference to any direction of time. This condition only states that the pairs of particles are uncorrelated. The probability density of two particles is the product of the two probability of one particles, the two probability densities of one particle. For Ufink and Valente, there is thus no Stochastic in Lanford's derivation, in the sense that the pre-collision condition has been removed. There is still a factorization condition, but which does not make reference to a direction of time. And that's why Lanford's theorem is so important. It allows one to derive the Boltzmann equation without the culprit in the original Boltzmann derivation, that is the pre-collision condition. This factorization condition, as we have seen previously, is involved in the last step of Lanford's derivation. It is required to go from the Boltzmann hierarchy to the Boltzmann equation. However, the Boltzmann hierarchy is not invariant under time reversal. So the factorization condition cannot be responsible for the appearance of irreversibility. And this condition is neutral with respect to the time direction. So now let's go to my claim. So my claim is that there are two crucial ingredients to obtain the Boltzmann equations from the Hamiltonian equations. And these ingredients are both involved in the crucial step that goes from the VBGKY hierarchy to the Boltzmann hierarchy. So let's begin with the first ingredient, which is the Boltzmann Grad limit. So this limit has been introduced by the mathematician Grad. It's the limiting regime for which the number n of Hart spheres tend to infinity. The diameter A tends to 0 in such a way that the quantity NA squared converges to a finite quantity. It's a limit for very diluted gases, since the volume occupied by bodies tends to zero. But there are still collisions, since the mean free path is finite and does not actually depend on the number n of particles. Some people have suggested that the Boltzmann Grad limit might be responsible for the appearance of irreversibility. Lanford himself suggested this interpretation. The Boltzmann hierarchy, like the Boltzmann equation, is not invariant under time reversal. That is, irreversibility appears in passing to the limit A to 0. So for Lanford, the Boltzmann Grad limit is the culprit. And this interpretation is very tempting, and I will partially follow it. More precisely, I claim that the Boltzmann-Grad limit is a necessary condition, but not a sufficient condition for the appearance of irreversibility in the context of the derivation of the Boltzmann equation. So to begin with, I stress that Giovanni also highlights the importance of this limit. In another paper, he says that we would like to stress that the Boltzmann-Grad limit is essential for the purpose of obtaining a rigorous derivation of the Boltzmann equation. And he indicates different technical reasons why the Boltzmann-Grad limit is essential. For example, this limit allows one to define a density probability on continuous variables in the Boltzmann equation from a density probability on discrete variables in the BBJKY hierarchy. The Boltzmann-Grad limit also prevents the factor in the collision term to not vanish when the diameter of hard spheres tends to 0. However, despite its importance, this limit is not interpreted as a time-asymmetric ingredient by Ufink and Valente. And to support this claim, they use another Lanford's work on the Vlasov equation. They emphasize that the Vlasov equation is time reversal invariant, although it's derived, like the Boltzmann equation, from Hamiltonian equations with an infinite limit. However, I have shown in my paper that this comparison is quite misleading since the derivation of the Vlasov equation does not actually use the Boltzmann-Grad limit. It only uses an infinite limit, but not the Boltzmann-Grad limit. There is not any A parameter for the diameter of hard spheres within this limiting regime. So the comparison of the two equations is not conclusive. However, I agree with Ufink and Valente that the Boltzmann-Grad limit is not sufficient for the appearance of irreversibility. And I have suggested maybe a more compelling argument that comes from the time symmetry of Lanford's theorem. As we have seen, Lanford's theorem is time symmetric. This means that it allows one to derive Boltzmann equation for positive times and anti-Boltzmann equation for negative times. And my point is just that the Boltzmann-Grad limit is used to derive both equations. So the Boltzmann-Grad limit cannot be a time asymmetric ingredient. If it were a time asymmetric ingredient, what could only derive the Boltzmann equation for positive times. But it's not the case. We can also derive the anti-Boltzmann equation for negative times. Okay. Nevertheless, I would like now to argue in what sense the Boltzmann-Grad limit contributes to the appearance, to the emergence of irreversibility. My point is that the Boltzmann-Grad limit breaks time reversal invariance of equations. Before using the Boltzmann-Grad limit, the hierarchy of equation is time reversal invariant. But with the Boltzmann-Grad limit, the hierarchy of equations is no longer time reversal invariant. And this is the case even if Lanford's theorem is time symmetric. Moreover, as we saw last week, without the Boltzmann-Grad limit, the Poincaré recurrence theorem holds. This theorem roughly states that the Hamiltonian system will return to a state very close to the initial state after a sufficiently long but finite time. By contrast, with the Boltzmann-Grad limit, the Poincaré recurrence theorem does not hold, since it lies on the assumption that the number of particles n is finite. So I think that this time reversal invariance breaking is very important for the debate on the emergence of irreversibility in the context of the Boltzmann equation. And we might explain this time reversal invariance breaking. there is indeed a very interesting property of the Boltzmann Grad limit, sorry, which is discussed by different people. It is the fact that the deterministic laws of collisions between two hard spheres no longer apply in the Boltzmann Grad limit. And the culprit is the diameter of hard spheres, which tends to 0. The collisions between two hard spheres are completely determined by the conservation laws. I mean, the energy, the linear momentum, and the condition that the momentum transferred in collisions is orthogonal to the plane of contact. By contrast, the collisions between two mass points with a 0 diameter is no longer determined. The extra constraint to define a plane of contact is missing. And this aspect might play an important role in the derivation of the Boltzmann equation. Indeed, let's go back to the crucial step in Lanford's derivation, I mean between the BB-JKY hierarchy and the Boltzmann hierarchy. The collision term CAK in the BB-JKY hierarchy requires the vector omega A12, that is the relative position between two hard spheres. This vector is involved in the collision integral. However, with the Boltzmann Grad limit, this vector, omega A12, tends to another vector, omega 12, which is no longer determined. And this vector, omega 12, is involved in the collision term CK in the Boltzmann hierarchy. And actually, I think that something happens at this point. And for François Golz, in the Boltzmann Grad limit, the vector omega 12 is now randomly distributed. It is no longer determined. And we find the same kind of considerations in different papers, actually, such as in another Giovanni's paper, when he emphasized that when the diameter of spheres tends to 0, the positions Q1 and Q2 of the centers of the two particles coincide, and hence the vector omega A12, with my notation, is no more defined. Therefore, the laws of collisions cannot apply in their standard form in the Boltzmann Grad limit. And similarly, according to Pierre Degon, in the Boltzmann Grad limit, the memory of the positions of the spheres before and after collision has been lost, and the vector n, which is omega 12, cannot be retrieved from the knowledge of the positions of the particles involved in the collision. So I think that this property might explain the time reversal invariance breaking in the Boltzmann Grad limit. Okay, that's it for the Boltzmann Grad limit.
Vincent, it's 45 minutes now.
Yeah, perfect. Thank you. I think, yes. So, but we have time.
Yeah, you can take even 10, 15 minutes. It's all right.
It's almost finished. So now I turn to the incoming configurations. So until now, I've claimed that the Boltzmann Grad limit breaks the time reversal invariance of the Liouville equation reframed within the BB-JKY hierarchy, but we have not finished. I turn so to the second ingredient for the appearance of irreversibility in Lanford's derivation. So we have seen that Lanford's theorem is time reversal invariant. But the problem with the theorem is that it allows the minus h function to decrease for negative times. I claim that the use of incoming configurations allows us to remove the part for negative times. By using the incoming configurations, we only keep the monotonic increase of the minus h function. So in that sense, the incoming configuration is a time asymmetric ingredient in the derivation of the Boltzmann equation. So that's the plan, and let me proceed. As Giovanni reported last week, there is a debate on the role of incoming or ingoing configurations. And I have to explain it before arguing for my claim. Very roughly speaking, incoming configurations are the velocities of our sphere before colliding. Conversely, the outgoing configurations are the velocities after the collision. And at some point in the derivation of the Boltzmann equation, it seems that we have the choice by using either the incoming configurations or the outgoing configurations. And this choice might be very important for the emergence of irreversibility because it introduces a preferred direction, a time direction. So the question is whether we really have the choice of to use ingoing or outgoing configurations to derive the Boltzmann equation. A crucial step in the derivation, there are many crucial steps, but a crucial step in the derivation consists in rewriting the right hand of the equations in the BBJKY hierarchy. More specifically, the crucial step concerns the collision term CA. During the derivation, this term is split in two integrals. The first integral, in the first integral, the velocities appear as ingoing configurations because of the domain of integration. And in the second integral, the velocity appears as outgoing configurations because of the domain of integration. And the step we focused on consists in rewriting the two integrals with only incoming or ingoing configurations. In a sense, it's just a change of variables in the second integral. We rewrite the second integral with incoming configurations. However, this change of variables, this mathematical transformation, has important consequences. And Lanford highlights the importance of this change of variables. We obtain the BBJKY hierarchy by systematically writing collision phase points in their incoming representations. We could equally well have written them in their outgoing representations. We would have obtained the Boltzmann collision term with its sign reversed. It's thus essential, in order to get the Boltzmann equation, to assume incoming collisions points x1, x2, and not outgoing ones. This is also what Cercignani and colleagues claim. In the derivation of the collision operator Q, we choose to represent collision phase points in terms in ingoing configurations. So the choice of ingoing configurations is a good choice. I mean, it is the right choice to obtain the Boltzmann equation. And without the use of ingoing configuration, either the collision term CA vanishes by symmetry, or if we choose to use the outgoing configurations, a minus sign will appear, leading later in the derivation to the anti-Boltzmann equation. Therefore, the derivation of the Boltzmann equation requires the use of incoming configurations. It seems to be a mathematical fact. And that is what Giovanni Valente claimed, and Jos Jufink and Giovanni Valente claimed in 2010, so 5 years before their paper. They say that the culprit for the emergence of irreversibility lies in the choice of the incoming configurations of collision points. So I think it's pretty clear, and I fully agree with this claim. So it seems that Lanford, Cercignani, Jufink, and Valente in 2010 are agreed on the role of ingoing configurations. However, Jufink and Valente changed their mind a few years later, so in 2015. Although they agree with the fact that the use of incoming configurations are essential to derive the Boltzmann equation, they claim that these configurations are neutral for the appearance of irreversibility, for the emergence of irreversibility. First, they mitigate the difference between ingoing and outgoing configurations for the derivation of the Boltzmann equation. So they say, the choice of either one of the two collision configurations does not make any difference at the level of the BBJKY hierarchy. One can derive the Boltzmann hierarchy from the BBJKY hierarchy rewritten in terms of either the incoming or the outgoing configuration without having to choose the right one. And I do not fully agree with this analysis. In particular, I do not agree with the claim that one can derive the Boltzmann hierarchy from the BBJKY hierarchy without having to choose the ingoing configurations. And let me explain why. Ufink and Valente indeed proved the equivalence for the BBJKY hierarchy. In the first part of the technical proposition 3, they proved that the BBJKY hierarchy with ingoing configurations equals the BBJKY hierarchy with outgoing configurations. And I am okay with that. I think it's really a great job and a very important result. Moreover, they emphasize that why the incoming configurations cannot be a time asymmetric ingredient. First, they show in the second part of the proposition 3 that the BBJKY hierarchy written with outgoing configuration is time reversal invariant. Secondly, they prove that in the proposition 2 that the BBJKY hierarchy written with incoming configurations is also time reversal invariant. So if the incoming configurations were a time asymmetric ingredient, they could not lead to a time reversal invariant equation. And again, I am also agree with that. But I claim that ingoing and outgoing configurations are equivalent to express, to formulate the BBJKY hierarchy in agreement with Ufink and Valente 2015. And this equivalence holds at the level of the BBJKY hierarchy. Nevertheless, and this is an important point, ingoing and outgoing configurations are not equivalent to derive the Boltzmann hierarchy and thus the Boltzmann equation. Why? Because we have seen, as we have seen above, the Boltzmann Grad limit, which is required in Lanford's derivation, constrain us to use the ingoing configurations if we want to derive the Boltzmann equation. And this is my main point. In other words, contrary to what Ufink and Valente claimed, we cannot derive the Boltzmann equation with the Boltzmann Grad limit by using the outgoing configurations. And again, this is a mathematical fact. This constraint is, for instance, claimed by the mathematician Laure Saint-Raymond. She says, at this point, the choice to express everything in terms of pre-collisional configurations and ingoing configuration is not really a choice. I have to express everything in terms of pre-collisional configurations. The use of ingoing configuration is not a choice if we want to derive the Boltzmann equation. It's not a convention, a mere convention. It's mandatory when we want to prove the convergence of the solution of the BBJKY hierarchy to the solution of the Boltzmann hierarchy. You cannot prove this convergence if you don't choose the outgoing configurations. So if you choose the outgoing, so if you don't choose the incoming configurations, the good configurations. I think we have to highlight, to stress the distinction between express the BBJKY hierarchy and derive the Boltzmann hierarchy. it's possible to use either ingoing or outgoing configuration to formulate the BBJKY hierarchy. There is an equivalence at this level, and I agree with Ufink and Valente. However, it does not follow that one can derive the Boltzmann hierarchy without having to choose the right one, I mean the ingoing configurations. And again, these ingoing configurations are mandatory and necessary to derive the Boltzmann hierarchy. And respectively, the outgoing configurations are mandatory to derive the anti-Boltzmann hierarchy for negative types. I think I have maybe 10 minutes, 5–10 minutes. To be fully clear, I do not claim that it would be impossible to derive the Boltzmann hierarchy by using outgoing configurations with other mathematical techniques. But as far as we are concerned with the current, the actual Lanford derivation, outgoing and ingoing configurations are not equivalent to derive the Boltzmann equation. So ingoing and outgoing configurations are not equivalent to derive the Boltzmann hierarchy because we have to use the Boltzmann Grad limit. But very briefly, what is the role of the Boltzmann Grad limit on this point? Why does it make ingoing and outgoing configurations non-equivalent? First of all, where does the equivalence between ingoing and outgoing configurations comes from at the level of the BBJKY hierarchy when we don't use the Boltzmann Grad limit? Ufink and Valente show that a continuity condition about collisions is responsible for this equivalence. This condition roughly states that the probability density of Hart spheres before collisions equals the probability density of Hart spheres after collision. And Giovanni discussed this point last week. It is the continuity at collisions introduced by Spohn. However, this condition, which makes BBJKY hierarchy equivalent, this condition is no longer valid when we use the Boltzmann Grad limit. So the equivalence between ingoing and outgoing configurations hold at the level of the BBJKY hierarchy, but not at the level of the Boltzmann hierarchy, which requires the Boltzmann Grad limit. And what is a bit surprising is that Ufink and Valente make these points very clear. They say, let us emphasize that continuity across collisions is a peculiar condition on the BBJKY hierarchy for Hart spheres, which does not carry over when we take the Boltzmann Grad limit, at least if one wishes, yes. So when the Boltzmann Grad limit is taken, we are no longer allowed to claim the equivalence between ingoing and outgoing configurations. Okay, that's my analysis of Lanford's derivation. And before concluding, here a summary of what I said about the derivation of the Boltzmann equation. So to be clear, so we start from the Liouville equation, then we rewrite the Liouville equation as a BBJKY hierarchy. Okay. After that, the BBJKY hierarchy can be expressed with the incoming configurations, or it can be expressed with the outgoing configurations. And these two ways of expressing the BBJKY hierarchy are equivalent. And I agree with Ufink and Valente on this point. Moreover, they are time reversal invariant, just as the Liouville equation and Hamiltonian equation. So far, so good. After that, we take the Boltzmann Grad limit, and in that case, from the BBJKY hierarchy expressed with ingoing configurations, one derives the Boltzmann hierarchy for positive types. Then with factorization condition, we end up with the Boltzmann equation. Now, if we take the Boltzmann Grad limit from the BBJKY hierarchy with outgoing configurations, one derives the anti-Boltzmann hierarchy for negative times. And similarly, with the factorization, we end up with the anti-Boltzmann equation for negative times. And my point is, again, also the incoming and ongoing configurations are equivalent to express the BBJKY hierarchy. They are not equivalent to derive the Boltzmann hierarchy. So it's not possible to go from the BBJKY hierarchy with ingoing configuration to the anti-Boltzmann hierarchy. And conversely, it's not possible to derive the Boltzmann hierarchy from the BBJKY hierarchy with outgoing configurations. Very briefly, just a few concluding remarks. The aim of the talk was to answer the question whether there is a time asymmetric ingredient that, added to the Hamiltonian equations of motion, allows one to obtain the Boltzmann equation. Yossiu Fink and Giovanni Valente offered a very insightful and very inspiring paper on this question. They argue that there is no such time asymmetric ingredient in Lanford's theorem. And I agree with this claim. I mean, there is no such time asymmetric ingredient in Lanford's theorem. However, we should make the distinction between Lanford's theorem and Lanford's derivation of the Boltzmann equation. And also, there is no time asymmetric ingredient in the first one, I mean, in Lanford's theorem. I claim that there is a time asymmetric ingredient in Lanford's derivation of the Boltzmann equation. More precisely, as I said, there is a twofold time asymmetric ingredient, the Boltzmann quad limit and incoming configurations. And we need both to explain the appearance of irreversibility in the context of the Boltzmann equation. Very, very briefly, first, the Boltzmann quad limit breaks the time reversal invariance of motion equations. However, it's not sufficient since we have two equations, one for the positive times and one for the negative times. We would like just the equation for the positive times. Here we need the second ingredient, the ingoing configurations, to derive the Boltzmann equation for positive times. If we choose the ingoing configurations, we don't have any longer the anti-Boltzmann equation for negative times. We removed the left part of the function. Accordingly, I suggest to interpret ingoing configurations taken with the Boltzmann quad limit as the time asymmetric ingredient in Lanford's derivation. My very last slide. So to conclude, I think that there is a new kind of Stochastic in Lanford's derivation. Fink and Valente made clear that the original Stochastic has been removed in the rigorous Lanford's derivation of the Boltzmann equation. There is only a factorization condition. However, the use of ingoing configurations play an essential role in the appearance of irreversibility in Lanford's derivation. So for me, there is a kind of Stochastic in this rigorous derivation. In a sense, we are in the same situation that Boltzmann in the 19th century. There is an ad hoc assumption to obtain the Boltzmann equation. However, it's not the same assumption that in the heuristic Boltzmann derivation. It is a weaker assumption. Unlike the original Stochastic, the factorization condition in Lanford's derivation can be assumed at the initial time and not necessarily at any time, as it is the case in the heuristic Boltzmann derivation. Indeed, the factorization property at the initial time is maintained in time with Lanford's derivation. It is a propagation of chaos property. In other words, according to my analysis of Lanford's derivation, one can view the out spheres as assumed to be uncorrelated at the initial time because of the factorization condition and before the spheres collide because of the incoming configurations. And if we put explicitly these assumptions in Lanford's derivations, we can derive the Boltzmann equation without any problem for negative types. Okay. Thank you very much.
Thank you, Vincent.
If you have any questions, of course.
Yeah. So
I will try to help you.
If you have questions or clarification or anything.
Yeah, I would have a question.
Yes, Hans?
Well, thank you very much for this interesting presentation. I must apologize that I come in here as an intruder. I have not been in the previous presentation last week, and I didn't have time to prepare very well because I only realized this morning that this interesting talk is going on, and I decided to jump in. So my background is I read the Lanford paper about 20 years ago or so, and I took something with me which convinced me somehow, and it's a one explanation thing. I mean, the confusing situation for me was there are so many reasons around, possible reasons. It's like if you get an invitation to a party and you don't want to go there, then you should never give 3 reasons, because everybody knows if you give 3 reasons, you don't have a single good reason for not going to the party. Yeah? So you should, for heaven's sake, only give 1 reason. And I think I tried at the time, 20 years ago, I tried to identify 1 reason which convinced me. And maybe I can describe it briefly, and then you can comment whether that fits into your way of thinking, or whether I misunderstood something, or whether my memory is fading after 20 years or so. Everything is possible. So I try it. There's something that, one reason thing which convinced me at the time. And it's about this grad limit, or you call it Boltzmann grad limit. It's described as n goes to infinity, and at the same time a goes to 0, like 1 over square root of n. And that is something that is true, but it doesn't really say so much about the limit, because I have to say, what do I mean with the limit? What kind of objects does converge? And the limit we are talking about is the limit of stochastic objects, because we start from Liouville, we have always distribution functions. So we deal with probability densities, and behind these probability densities, there are random variables. And random variables come with very different types of conversion. I mean, the whole thing of probability theory is the story of the interesting parts of probability theory are convergence theorems, the central limit theorem. I mean, the whole thing of stochastics is designed such, with the Kolmogorov approach for probability theory, that you can have convergence results. So it's very important to note that you cannot just say it's grad limit and it's something about n and a. It's what kind of objects do have to converge, and these are random variables. And there are very different concepts of convergence for random variables. The weakest one is convergence in the mean. There could be a quadratic convergence. There could be a pointwise convergence, almost sure. And so there are different concepts of convergence for a stochastic object, no matter what kind of limit in detail I do. That's always n goes to infinity, and I have some sequence of random variables, and they are not equally strong. So from some of these concepts, you can follow that you have, if you have convergence in that sense, you have it also in another sense, but not vice versa. So this is a very natural situation. People in stochastics, they really do a lot with convergence theorems, and they are always very careful to say what kind of convergence they mean. And some theorems are correct only if you use the proper concept of convergence with it. So that's the background. And now how I understood the work of Oscar Lanford III is that, yeah, he proves something for a very short time, as he emphasized. He starts from an initial condition which is factorized, and then he wants to show that it remains factorized, and that at the same time, over this short period, something like an entropy increases. So that's the exciting news. Now, what I did at the time is I tried to understand the concepts of convergence, because this limit, which you take as a passage from the BBGKY hierarchy to the Boltzmann hierarchy, that is the limit. I mean, that's the step at which the stochastic limit takes place. So that's the limit of probability densities or random variables. And so in what I remember is that the concept of stochastic convergence for the initial conditions is a stronger convergence than you get for the conditions after a time t. So, and that's my point. I mean, that is my one and only explanation why there is no paradox. There is a stronger concept of convergence or stochastic convergence in this Boltzmann Grad limit, and there is a weaker concept of stochastic convergence. Again, another Boltzmann Grad limit, but for the objects random variables that can come in different shades. And so the input configuration has a stronger conversion than the output configuration. And that's why I actually cannot continue either forward in time or backward in time, because the final condition doesn't really satisfy the strong type of assumptions that had to be made for the initial conditions. So that's how I memorize the situation. It fits together with a lot of things you have said, but it's a little less emphasis about incoming or outgoing. It's initial conditions and strong conversions, and final conditions and the weaker type of conversions. The only contradiction to what you said, which I can recognize, is that if I continue after I have the final result, if I want to continue, I think I can continue neither forward in time nor backward in time. You said I only can not continue backward in time, but I could continue forward in time. That is against what I remember after 20 years. Otherwise, I think the explanations I gave are pretty much in accordance with what you say. It's just that I would de-emphasize this Boltzmann Grad limit and rather emphasize the strengths of the stochastic convergence in the respective initial and final Boltzmann Grad limits, which are two different limits. So can you get anything reasonable out of that kind of story?
Thank you very much for your comment, but I'm very sorry because I'm not a mathematician, and I'm not sure to have a clear answer to your question, which is for me quite technical. I'm a philosopher. I'm not a mathematician, but I think it's a pity that Giovanni is not here, because maybe he could help me to answer to your question. So maybe you can send him an email, and also watch his talk, because watch his talk last week, because he gave some technical details on why we cannot prove the Boltzmann the Lanford theorem backward. Why we cannot prove the Boltzmann equation backward in time. But on the kind of on the question of your stochastic convergence, and I'm very sorry, but I cannot help you.
So you don't know also that there is anybody who would argue along those lines. Yeah? I mean, once one is aware of this idea that stochastic convergence comes in grades, in steps, in strengths, then this is a very natural explanation. And stochastics people are aware of that. I'm not a mathematician either, yeah, but I happen to know these things because I think one should have a background in stochastics anyway. And so, yeah, this kind of argument never appears in the philosophical discussion. So,
yeah, I don't know. I've never seen this kind of discussion. So I would be very happy to read your paper. And,
oh, I don't have any paper. I read the Lanford paper, and that was my explanation, and then I was happy and left the thing.
Yeah, maybe there's some discussion about stochastical convergence, but I'm not aware of this discussion. Sorry.
Okay, thanks.
I don't know if there's anyone who wants to jump in on this. I sent the link of the video, Hans, in case you want to have a look. It's on the chat. Okay, thank you both. So next one on the list is Aurélien.
Okay. Okay. Yes. Thank you. Thank you very much for this nice and very clear talk, and it was very, very. I mean, the explanation was very, very illuminating because you put it very slowly, all elements. So I try to. I think I understand a bit better the problem than before, because the issue for me is very curious, because this model that is this Lanford's theory is very, very idealized. This Boltzmann grad limit is so much peculiar, and it looks like indeed you're probably right that when you're breaking the symmetry between the past and the future by using these kind of things, because you mentioned during your presentation that you cannot use the Loschmidt objection, and that's for me very, very strange. If you cannot do that, it probably says that a lot about the limitation of the full derivation of Lanford, because even though it's very beautiful, it looks like somehow the theory probably is used on this also on this limitation of the art sphere problem, but you cannot apply it to. You're probably in two classes of problem which are separated by the choice of the ingoing conditions that Lanford is using. So it reminds me a bit like something that is used in quantum in quantum electrodynamics, when you want to derive some of the macroscopic electrodynamics with dissipation, and when you try from the basic Hamiltonian formalism of quantum electrodynamics. And one thing is which is appearing is that when you use a large number of systems, infinite number of systems, you indeed break this symmetry, and you cannot apply, for example, this Poincaré recursion recursion theorem. And then you have also a lot of problem with applying Loschmidt's paradox, because you somehow, it was symmetric at the beginning, and then at the end you have two ensembles of two systems which cannot be easily connected. In quantum field, it's very often like that if you are going to using this kind of limits, when you are doing infinite number of elements, you get a very large space, and two domains of the Hilbert space, for example, are separated, and they are not anymore connected. Even though originally it was possible to go from one to the other, now it's not anymore because of the limit. Probably the Boltzmann grad limit is playing the same role in this theory. And also, it's another last point is, I think I discussed that last time as well. It was about the iteration of the theory. It's applied at one initial time, but you cannot easily, for me, apply it to another time, because as you show, the curve of the entropy is strange. At the initial time, you have a slope which is positive in one side and negative in the other side. Yes, this curve. For me, it reminds me things like which is probably connected to this idealization that that is used in the Lanford theorem. This is Boltzmann grad limit, and which is probably together with this ingoing conditions breaking completely the symmetry. It's not completely clear in my mind, because I don't study so much this as you, but it seems to be very convincing what you say about the problem of this Boltzmann grad limit. I don't know if you can if I can help the discussion, but anyway, I enjoy it.
About the Boltzmann grad limit, I perfectly agree with you. It's a very strange limit, and I'm not sure that this limit has a physical meaning, and but my project was to try to answer the question whether Lanford's theorem explains the emergence of irreversibility. So that's why I am forced to study this Boltzmann Grad limit. But you're right, maybe the problem comes from this, I mean, many problems come from the use of this Boltzmann Grad limit, and maybe we should not use this limit to modelize some systems, or because it's very idealized, and you agree, but the fact is that Lanford's derivation requires this Boltzmann Grad limit, so we have to try to understand the role of this limit in this derivation. And so maybe if the Boltzmann Grad limit is a culprit, or one of the culprit for the emergence of irreversibility, maybe we should not use this Boltzmann Grad limit also. But we don't have any more the Lanford.
Yeah, that's a problem.
But I think there are different philosophical questions. I think a question concerns the physical ingredients for the emergence of irreversibility. Why? How irreversibility? How does irreversibility? Sorry, come from a reversible n system? I'm not sure that Lanford's derivation gives answers to this question. I think Lanford's derivation is a nice derivation to discuss the problem of how physical theories articulate between each other. I mean, it's more for the, I think it can help to answer the question of the reduction of kinetic theory of gas to classical mechanics, more than to solve the problem of irreversibility. I mean, the physical problem of irreversibility, because the Lanford's derivation is very formal, very mathematical, and I'm not sure that it is very helpful for maybe physicists, but I think it's very helpful for philosophers who are interested in how kinetic theory of gas is connected to classical mechanics. And this derivation shows that the connection is not straightforward at all. We need very strange tools like the Boltzmann Grad limit, and we also need ad hoc hypotheses like incoming configurations if we want to remove the wrong part of the minus h function. So yeah, I'm not sure to answer your question, but
no, I think I think yes. You answer. For me, what is very interesting is that it is a theorem that you can analyze already. There are not so many deep results like that in this approach of in kinetic theory. It's difficult to have final result, and so if you have the Lanford theorem is already something that, as you say, is a gem. So it's very, very precious result, but for mathematicians certainly. But it can help probably for physicists to think about the limitation of this kind of models, and maybe the infinity is a source of the infinity, and the convergence is used in the theory is a problem, as it was discussed before. But I have really the feeling that by using this kind of domain of infinity, you separate, you break the symmetry between between different sectors of the theory, they are not anymore able to communicate easily, and then it takes maybe more. If you cannot apply the Log-Schmidt, for example, objection, it says to me that something is strong about that. Yeah.
And you said that the fact that you cannot apply Log-Schmidt's objection, you said that it is a problem for you.
But for me, yeah, because it looks like it's about like you said about the chaos. It looks like at the beginning you start from a certain space of your a phase space for the position and the configuration space, and then if you reverse the motion, you say you show a sketch with the arrow with two arrows. If you reverse the direction of time, then you will need it will be looking like a conspiracy in order to get the motion back, and you show that in your presentation. So it's clear that somehow you have already here a kind of postulate about. Yes, exactly. Yeah. You have a clear postulate about probably it's connected to how complicated the system is because you have infinite number of particles.
An infinite number of particles is, on the one hand, it is the solution to have a rigorous. The way to have a rigorous derivation of the Boltzmann equations, but on the other hand, I agree, it comes with other problems and other specificities with infinite systems. And I think it's interesting what you say about, I mean, people mostly are happy with the fact that we cannot apply Log-Schmidt paradox with Lanford's derivation, since it seems to explain us why, how to solve the paradox, because the paradox vanishes with Lanford's derivation. But I think it's interesting to see that for some other people like you, it's more a problem than a solution to avoid Log-Schmidt's paradox. Thank you. I will think about it.
Thank you for the presentation. I like very much the discussion. Yeah.
I don't know, Aurélien, if you have another question, but okay. So can you wait? I have two people on the list and ask your question later.
Yeah.
Okay. So next one is David or David. I don't know which one is correct.
Hi, David. Should be David.
Okay. Hi, David. You can go next.
Hi. So thanks, Vincent. It's really nice. So I wasn't able to attend the other talk, so I'm not really, I probably don't have the background, but from the information that I gained from your talk. So the Boltzmann Grad limit somehow actually allows you to, so in a way you say, somewhere in your talk, I saw that somehow it guarantees some sort of irreversibility because you don't have this objection by Zermelo, in the sense that you don't have the, but there is this recurrence theorem doesn't hold because of the infinite number of particles. But I also see that there is a constant cross section. So n goes to infinity, a goes to 0. There is a constant cross section. I don't see how. I mean, is there a way? Can you elaborate on how to on Log-Schmidt paradox in Boltzmann Grad limit? Because it seems that it looks to me like you cannot diffuse it. Like you still have like a. If you run times backwards, then you're gonna get. You're still gonna get like. It seems to me like the Boltzmann Grad limit is still time reversible somehow. See what I mean?
I'm sorry, I don't see what you mean. Can you explain your question, please?
So during the talk, at some point it is said that that this Boltzmann Grad limit can be understood as a source for irreversibility because you've got that the Poincaré recurrence theorem doesn't hold, probably because of the number of particles close to infinity. On the other hand, the cross-section for particle collision remains constant. So I don't see how, if you run time backwards, we shouldn't be able to. I mean, you could have some sort of a Loch-Schmidt objection to it anyway. Is this any clear?
So I've tried to make clear that the word of the Boltzmann Grad limit concerning irreversibility is that this limit breaks time reversal invariance, but it does not explain the emergence of irreversibility.
Okay, so the Loch-Schmidt paradox somehow is a paradox in that limit.
I think things are complicated, and as far I understand Lanford derivation, I mean, we cannot apply Lanford's theorem backward in time, so we avoid Loch-Schmidt's paradox. But it does. The fact that we cannot apply this theorem doesn't mean that this is a source of irreversibility. I mean, the microdynamics maybe it is possible to invert invert particles, and we have this reversible microdynamics. But you cannot derive the Boltzmann equation. So, I mean, again, it's an impossibility at the level of the mathematical level, but I don't know what are the conclusions, what are the consequences on the physical level.
Comment directly on that?
Excuse me?
Yes, yes.
I would have a comment directly on the question of David. I'm not sure whether I get it right, but let me try. Maybe have an additional ingredient. I mean, the way you argue, you say that even if the number n becomes very large, the time for collision stays the same. I mean, that's the construction of the Boltzmann Grad limit. Yeah. So you say it doesn't really help because each particle reacts during that fifth of a mean-free path anyway, and so it's kind of the same situation, and that's why you don't see why certain paradoxes should not arise in the one case or not so easily as in one case as in the others. I agree. A certain fraction of particles would be reacting or it would be colliding within that period of time. But don't forget the recurrence theorem is about the n particle system to return to the same state as in the initial condition. That's in an incredibly long time. And that time scale increases with n. So it's not about what an average particle sees. I mean, we can go into mean field limit by this kind of Boltzmann grad, and for every particle, it's kind of always the same. It's the same collision time. But for the overall system, the recursion time goes to infinity in this limit. And so the argument is never applicable because you're restricted to 1/5 of a collision time. That was the value you had given. And the recurrence theorem is about incredibly long times, actually infinitely long times, and the limit n goes to infinity. So there cannot be a conflict between the two. That would be my tentative explanation.
Yeah.
Okay. So,
and just a remark. Actually, the Poincaré recurrence theorem is not really important in Lanford's derivation. I mentioned this point, but what is important is that the Boltzmann Grad limit breaks the time reversal invariance of the hierarchy of equations. But yeah.
Okay, and this is the part that I don't understand because so like I said, I didn't attend the talk by Giovanni Valente. So I really don't know much about Lanford's theorem, but what I wanted to understand is to see to me if I'm not really, let's say I'm only interested in understanding whether the Boltzmann Grad limit is respects time reversal or not. Because as far as I can see, the Loch-Schmidt paradox is still a paradox in this limit. Is this correct? I mean, I'm not even talking about Lanford's theorem.
In which sense is it still a paradox? I mean, in the box.
So if you have n particles, even if n tends to infinity, if you cross section is the same. So, well, at some points you were talking, you mentioned, and this is something that I found really, really interesting. Because I think that might be the key to it, is that whenever you're doing scattering calculations with particles with radius pointing going to zero, then scattering is intrinsically probabilistic. So you cannot really, there is some randomness jumping into the problem there.
Yes,
that might be the key there. But, I still from this constant cross section, I think about moving like switching time backwards, and then I would still, you know, I would still be having, you know, this kind of a Lock-Schmidt kind of objection.
yeah, I think I'm not sure, but we can imagine that we can apply you can apply the Boltzmann Grad limit and reverse velocities and see what happens. And in that case, I think you write Lock-Schmidt. I don't know what happens with Lock-Schmidt paradox in that case, but maybe this is your question. But
yeah,
what I said is not about using the Boltzmann Grad limit, but is about Lanford's, what we learned about Lanford's theorem on Lock-Schmidt's paradox. And he says that we cannot apply, I mean, Lock-Schmidt's paradox does not hold. But you're right, an interesting question also is, so we forget Lanford's derivation. We have a hard sphere gas. We take the Boltzmann Grad limit. What about Lock-Schmidt's paradox in that case? Maybe this is your question? No.
Well, my question is about
and
I just want to know whether, you know, Boltzmann Grad limit is to what extent it's a source for time irreversibility.
I think it's a very good question, and yeah.
This is not. I'm from a different background, but that's still.
But yeah, I will think about it. But yes.
Okay. Thanks.
Rafael, you wrote a question, but if you want to ask, you can.
Okay. Yeah. So thanks for the talk. It was really, really clear. So thank you very much.
Thank you.
Yeah. So as far as I understand, you explained us that you cannot derive both in the same time, like the Boltzmann and the anti-Boltzmann equation, like they are incompatible. But so I guess that's a reason to think that you should where the time asymmetry is coming from. But then what I'm not sure to understand is okay, but what we observe is that entropy is always increasing. So it looks like we need to take the choice of the incoming configuration. But how do you account for this choice? Is it an hypothesis to consider that we need to take the incoming configuration, or can you justify it in some way?
It's a very good question. I think it's a natural question. So we observe, of course, the entropy increases. So that's why, in order to make Lanford's theorem or Lanford's derivation empirically adequate, we have to assume ingoing configurations. And you ask me, but do we have a physical reasons to explain this choice? Another reason that just to be empirically adequate. And I think it's a very good question. I don't have, and I think Giovanni is concerned with this question in this talk. His question is in what sense incoming configurations are physically relevant to explain the emergence of irreversibility. And he claims that he don't see any reason why incoming configuration would are explanatory with respect to the emergence of irreversibility. And I have no answer, but I think it is still a very good answer to say we want to have an empirically adequate theorem. So, and that's why I said, I think in a sense, we go back to Boltzmann's discussion. Boltzmann introduced the Stochastic Ansatz in order to obtain irreversible, to obtain the Boltzmann equation and the emergence of irreversibility. But why he introduced this Stochastic Ansatz in order to have an empirically adequate result. And I think it is the same problem here, or the same debate here. We have to assume incoming configurations to have empirically adequate Lanford derivation. And but I agree, it's not fully satisfactory for a physicist. I agree with you. I don't have any answer. So that's why I also agree with you, Fink and Valente, that we are not happy with this with Lanford's derivation, because there is something which is missing in this derivation if we want to explain from a physical point of view how irreversibility appears. Yes, we are not happy with this. We are not fully happy with this derivation.
Okay, yeah, that was what I was thinking, but yeah, I see your point. And
you're perfectly right. And I think so. The problem of Boltzmann with the Stochastic Ansatz is the same problem with Lanford's derivation, even if Lanford's derivation is better, is more rigorous, and the Stochastic Ansatz, the new Stochastic Ansatz, is weaker because we don't have to assume at any time, but just uncorrelation at the initial time. But still, we don't really see why the physical reason to assume incoming configuration and not outgoing configurations. Yet, maybe in the future we will understand. But if you can help us,
okay, thank you very much.
Vincent, it's like kind of a follow-up actually. I was wondering if you think that relating to that, if you have the impression that the answer might also be related to the failure of the continuity assumption in the case of the BG limit. So if you can go to one of the last slides, just so we of the final one. Sorry, go in the other direction.
Which slide? Excuse me.
I think it's around 65 or something, but I might be mistaken. So it's so they have a there's a one of the last quotes from Uffing and Valente. Yeah, the previous one. Okay, so here basically they admit that the continuity is something that is crucial to have this. Yes. But so and this is something that doesn't it's not given in the case of the BG BG limit, right? So I was wondering if there is, if I don't know, if you had the impression that there is something there. There is something about this continuity. I don't know, just super bold hypothesis.
But yes, this is another strange behavior with the Boltzmann Grad limit. So the Boltzmann Grad limit breaks time reversal invariance of equation. Boltzmann Grad limit does not hold for this continuity across collisions. Boltzmann Grad limit lead to undetermined laws of collision. So another strange consequence of Boltzmann Grad limit, but I don't have any very good ideas on this point. Yes, no.
Yeah, I agree. It's weird that they recognize this and then they say that the incoming configuration is not. It's weird. It would be nice to have Giovanni here to ask. Aurelian, did you have a further question, or someone else?
Yeah, I mean, the point that you mentioned about the continuity is interesting. I wonder what Boltzmann would think about that, because in 19th century they had a lot of discussion about this kind of issue. You know probably this problem about the Norton dome, which is recently discussed in literature about this this curious feature of some deterministic dynamic, which sometimes leads to a priori stochastic or at least non-deterministic feature, because they fail to fulfill some conditions of continuity and things like that, and I think Lipschitz continuity and things like that. And it's at that time it was discussed, and Boltzmann was thinking about this kind of issue. I think in some philosophical paper, I don't remember which one. I have to find that in my bibliothèque. But one of the motivations, it seems that he was discussed about what is called Volterra. Later it was called Volterra equation, this integral differential equation, when you have some time to integrate over all the past of the system to compute the dynamic instead of having an instantaneous process. So and well, it would be interesting to see if Boltzmann didn't think about the role of continuity in his problem, because it seems that really it was one of the reasons for trying to find better models for him was to remove some of the issue with continuity and so I prefer personally the Boltzmann intuitive picture of reality than the complicated Lanford theorem, but even though it's much less rigorous, but as this is probably because I'm a physicist, but at the end, what you show it very clearly is that when you at the end, the last slide of your talk is that at the end you have also some postulate. You have to assume something in the Lanford theorem, which are not so far finally from what Boltzmann want assume. So now it looks like you have to find either a finite model, so with finite number of particles. It will be good for me, because infinite number of particles is always difficult to digest, and especially this cross section, which is going to zero. It looks like the probability of having a collision is going to zero, so it's very improbable to have an event. At the same time, you have an n number which is very large, so the probability is not zero. So you're compensating the vanishing probability of an event by a large number of particles. This is I don't know if it makes sense, but maybe it's the source of all the problem.
And if I can just add 1 second, Vincent, before you reply, that was actually something I was thinking about what you were saying about reduction, which is the main interest you have there. And there is this idea of idealization that in this case seems to be very important. So how much can you idealize to make the case about reduction? So I just wanted to jump in to ask a more general question about this idealization. And whether, you know, how much would you be happy to accept it in this case? I don't know.
Yeah. First, to answer to Aurélien, I think it would. I agree with you. I would prefer to have a rigorous derivation with a finite system, and it would be marvelous to have a rigorous derivation of the Boltzmann equation in a Boltzmann's way, I mean, for finite systems. Yes, it will be very, it will be, yeah, more, yeah, a very good derivation, but we don't have this derivation. That's why we have to pay attention to Lanford's derivation, and which requires the Boltzmann Grad limit. But maybe in the future, I mean, we will derive the Boltzmann equation without the Boltzmann Grad limit for finite systems. And I think it, yes, I hope, but, and about the question of idealizations, yes, you what, and John Norton also discussed the role of the Boltzmann Grad limit in his 212 paper, and he argued that it's not a good idealization to, I mean, to to modelize some systems. But again, unfortunately, it is used in Lanford's derivation. So I agree that many problems come from this Boltzmann Grad limit. And yes, so when I discussed the fact that collisions become indeterministic in the Boltzmann Grad limit, this point is already discussed by John Norton in his paper. Actually, I found this this reference in his paper when sorry, where is it? Yes, this so Norton says that.
And this is the reason why Norton believes that this specific kind of idealization is not a good one. So the failure of determinism. That's the reason he
yes, that's how I understand his paper.
Okay. I'd be nice to read this paper if you can send it along.
Yes, of course.
Okay, we have 2 minutes if someone has a last remark or clarification or something. Otherwise, we can just thank Vincent, who might be tired. Thank you a lot.
Thank you very much.
I really enjoyed that. Thank you.
Thank you.
Thank you.
Thank you very much.